Hi everyone, welcome to my channel. In this video, we're going to talk about food technology, in particular chapter 2, the control of water activity. And we have done section 2.1 until 2.3 in the previous weeks. So in this video, we're going to focus on section 2.4 until 2.6, where in 2.4 we talk about water activity and enzymatic reactions, followed by water activity and chemical deterioration of food, and prediction of water activity value in practical or industrial applications. So for the first one, water activity and enzymatic reaction, just a brief introduction on the role of enzymes, especially in food processing. As we know that enzymes are biological catalysts that are present in all living organisms, they play a crucial role in food processing by accelerating chemical reactions without themselves being consumed in the reactions. Enzymes are also highly specific, meaning it has a specific substrate to work on a particular reactions, and its enzyme targeting a particular substrate to catalyze a specific reaction, the reaction. In food processing, enzymes are utilized for various purposes such as improving texture, enhancing flavor, accelerating ripening process, as well as facilitating digestion. Enzymes are therefore an integral part to many food industries, including baking, brewing, dairy, and food processing. There are, of course, some factors influencing the efficiency of the enzymatic activity. One being the temperatures, where enzymes have an optimal temperature range for activity beyond which they will denature. The ideal temperature for enzyme is usually between 20 to 25 degrees C, where below this temperature they tend to become inactivated, and conversely at higher end at very high temperature such as 45 degrees C, the enzyme tend to get denatured or destroyed. It's worth mentioning that low molecular weight enzymes tend to be more heat stable than higher molecular weight enzymes, probably due to the higher surface to volume ratio, and these low molecular weight enzymes are easy to dissipate high temperatures, and therefore they tend to be more stable. The other factors is pH, where enzymes function optimally within specific pH range, typically between 6 to 8, and deviation can impair their activity, meaning if it is beyond or less than this optimum range, the enzyme activity will be affected. The other factor is substrate concentrations, where enzyme activity is typically proportional to substrate concentration until saturation occurs. In other words, if we are running out of a substrate, then the enzyme's velocity or kinetic is no longer linear or proportional. The other factors is inhibitors, the presence or absence of certain compounds that can inhibit or deactivate enzymes will impact their functionality. And therefore, understanding of these factors is essential for controlling enzyme reaction in food processing in order to achieve desired outcome. So how people control enzyme reaction in food preservation and for quality maintenance? Well, as we know that enzyme reaction can lead to undesirable changes in food quality and safety if left uncontrolled. Therefore, controlling this enzyme reaction is crucial for preserving the freshness, the nutritional value, and sensory attributes of our food products. This reaction includes enzymatic browning, lipid oxidation, and protein degradation are typically the common enzymatic reaction that can affect food quality negatively. Uncontrolled enzymatic reaction therefore can result in color changes, off flavors, texture deterioration, as well as nutrient loss. Effective control of enzymatic reactions can extend the shelf life of our foods, ensuring consumer satisfaction and reducing food waste. Strategies include temperature control, pH adjustment, enzyme inhibition, and water activity management. The next thing is we're going to talk about is the activity or water activity and the stability of the enzyme. So water activity or AW, A sub W, refers to the availability of water molecule for chemical reaction, for driving chemical reaction as we know from the previous weeks. And this available water molecule also affect microbial growth in the food system. Enzyme stability is crucial for maintaining the functionality and efficiency of enzyme in food processing. Water activity therefore plays a very important role in modulating enzyme stability, affecting their conformation and activity. The denaturation of enzyme can happen or usually involve the alteration of 3D structure of enzyme, therefore leading to the loss of their catalytic activity. And this may result due to high water activity, which can promote enzyme denaturation by disrupting hydrogen bonds and hydrophobic interaction within the enzyme structures in the presence of higher amount of free water molecules. Denaturation of enzyme can also result in irreversible loss of functionality, rendering them ineffective in catalyzing the biochemical reactions. Factors such as temperature, pH, and presence of denaturing agent can exacerbate the denaturation process under high water activity conditions. Stabilization of this enzyme is therefore important in order to control and maintain food quality. Stabilization here refers to the preservation of the native conformation and functional integrity of our enzyme under varying environmental conditions during food processing. Low water activity environments can contribute to enzyme stabilization by minimizing water-mediated structural changes and preserving enzyme substrate interaction. There are some strategies for enzyme stabilization. These strategies include formulating food system with reduced water activity level through processes such as dehydration or addition of compatible solids. Secondly, utilize stabilizing agents such as salts, sugars, polyols to mitigate the effects of high water activity on enzyme stability. And thirdly, employing encapsulation techniques to protect enzyme from water-mediated denaturation and maintain their activity during processing and storage. In the following diagram, in this diagram, we can see the relation between water activity on the horizontal axis and the moisture content on the vertical axis. As you can see, water activity influences not only microbial spoilage but also chemical and enzymatic reactivity or reaction. Water activity may influence chemical reaction in different ways. It may act as a solvents or reactants or change the mobility of the reactants by affecting the viscosity of the system. Water activity influences non-enzymatic browning, lipid oxidation, degradation of vitamins and other nutrients, as well as enzymatic reaction, protein denaturation, and starch gelatinization. Typically, as the water activity level is lowered, as you can see from this graph, the rate of chemical degradation reaction decreases or reduces. Couple point worth noting here, as you know from the previous lectures, the higher the activity, let's say in the 0.9, these microbial such as yeast, bacteria, and molds start to grow. even though the moisture content is actually low. Okay, and the more water activity, meaning the more free water molecule present, such as 0.95, 0.96, then bacteria, you start to seeing bacteria to grow. And the other thing is enzyme activity, as you can see here, start to um, play a contribution at water activity around 0.6, let's say 0.6 onwards. Whereas browning reaction also approximately between water activity of zero point 0.5 and zero point 0.7 approximately, in which case after that the browning reaction tend to decrease and followed by other enzyme activity beyond 0.7. And in water activity between zero point 0.3 and 0.5 here, we tend to have loss of crispness of the food, powder caking, and collapse of food structure. Lipid oxidation tend to decrease between 0 and